300 years of calculus and nobody saw this. Why is that? Well, my guess is nobody ever thought about using the hockey sticks, right? Who would use that? Option traders would use that. Option quants would use that. Hi everybody, I'm Doug Costa. I'm a quant here at Susquehanna. My background is in mathematics. I was an undergraduate math major. I went on to get a PhD in mathematics, specializing in abstract algebra. When I finished my PhD in 1974, I was lucky enough to get a position as a professor in the Department of Mathematics at the University of Virginia, where I taught and did research for a number of years. In 1993 or so, through a former grad student, I became a consultant for Susquehanna, helping with mathematical questions, and that led to a very good relationship. And in 1997, I joined the firm full-time as the head of the quantitative research department. And I held that position until mid-2015, when I transitioned into a role in our education department. We have a very highly developed education department, and I now do a lot of teaching in that group. So today I'm going to show you some of what we talk about here concerning the VIX. This is the SIBO, the Chicago Board Options Exchange's S&P 500 Volatility Index. So it's an index that was designed to try to measure volatility, which means standard deviation of returns of the S&P 500 index. Now, the exciting thing about this is that the financial engineering technology that was used to create the new VIX, there's an old VIX and a new VIX, we'll talk about that. This financial engineering technology, it was invented in the 1990s to model variance swaps, as an effective way to model variance swaps. And it really is quite pretty, mathematically speaking. So that's what we'll be talking about today. Okay, so the story begins with the old VIX. So this is pre-2002, sometime in the 1980s, I'm not quite sure when. The SIBO decided that they would like to publish a volatility index, and it was supposed to represent nominally the volatility over the next 30 days, so kind of predicting future volatility. And the tools they had available then were not as well developed as tools we have now in financial engineering. So here's what they did. Since the S&P 500 index futures trade on the SIBO, that this was their product, the options on those futures are European style. So an important thing about being European style is that they can be priced using the Black-Scholes formula. Now, doing so means that you're going to use the Black-Scholes formula. So for example, for a call option with strike K and maturity T, which I have written here, the inputs to the Black-Scholes call formula are the current price of the index, which I've written S0, and typically when we use Black-Scholes, we use S here because it's generically for a stock price, but in this case it's the index value, the S&P 500. The strike price K, or exercise price, the maturity T, the risk-free rate R. This Q we use as the dividend yield, if there is a dividend yield, and sigma is the volatility of the index. And in Black-Scholes, the assumption is that the volatility is some constant. The Black-Scholes formula is this formula here. It's S0 e to the minus QT, big N of D1. Big N is the standard cumulative normal distribution function, minus the strike K e to the minus RT, big N of D2. And D1 and D2 can be computed this way. I'm using the notation that you will find in John Hull's wonderful textbook, Options, Futures, and Other Derivative Securities, and that's a standard book that we refer to. Okay, so the idea of Black-Scholes implied volatility is that you have this formula, and it postulates that if you know the volatility, then that should give you the price. Well, the idea of implied volatility is to say, I definitively know the price of the index, I definitively know the strike of my option, the maturity of my option, the risk-free rate, and the dividend yield. I don't necessarily know the volatility, but I can look at the market price. Where is the option trading? Where's the call option trading? And then I can try to do a search. You can do a simple binary search to find the sigma, the unique sigma, that will produce that market price. And then that is called the Black-Scholes implied volatility for this particular option with this particular strike and this particular maturity. So the people at the SIBO, I guess, thought, well, yeah, we can use Black-Scholes implied volatilities as our index. Now, this raises the question, what strike and what maturity? Well, they wanted the maturity to be nominally 30 days. So there's also the Black-Scholes formula for put options. So we have call options and put options. So they wanted to incorporate both of those. So what they decided to do was find strikes nearest the forward for a given maturity, and then let sigma k be the at the forward implied volatility. Now they're going to find that by calculating the call and the put volatility and dividing by 2. So that'll be the average of those two will be the implied volatility they use for that particular maturity. The problem with the 30-day nominal maturity is that on any given day, there may or may not be an expiration exactly falling 30 days in the future. So typically they're not. So what they decided to do is find the two expirations, capital T1 and capital T2, surrounding the 30-day point in time, and then calculate an implied volatility for T1, an implied volatility for T2. And now you have the problem of how do you mush those together to get a 30-day implied volatility. So here's what they did. They said, okay, these volatilities in Black-Scholes, let's go back to that for a second. The Black-Scholes formula, these volatilities that we get are annualized volatilities. That's the input to the Black-Scholes formula. And that means that volatility corresponds to the volatility you would see over the course of 1 year, or for annual returns. So in the time period T1, the actual variance realized is sigma T1 squared times T1. Sigma T1 squared would be the variance for a full year. T1 is part of a year, or some fraction of a year. So this product is going to be the total variance indicated by that option price, or the put and call price averaged. Similarly, calculate sigma 2 squared T2. Oh, that should be a 2 there. Sorry about that. And then use time linear interpolation of variance. So what's the idea behind time linear interpolation of variance? Well, the idea behind that is a belief, basically. If you believe that disjoint intervals of time produce independent changes in the index, then the variances should add, which means that over time, if you chop a time interval into, say, n equal size intervals that are disjoint, then in each interval you have independent changes in the index, and those variables give you independent returns. The variance of the sum of those returns is the sum of the variances because of the independence. And that means that the total variance should be proportional to time, and that would justify time linear interpolation of variance. Well, you could reasonably disagree with that and think, well, maybe those movements in the index are not independent from one time interval to another. Maybe there's some autocorrelation. Well, yes, we can worry about that. However, this assumption gives us a nice way to get to a good formula. So for the 30-day, if my t now I set at 30 days, then I can do this time linear interpolation. Here you have standard linear interpolation. We're interpolating the variances, so we put the variances there. And then the interpolation coefficients are T2 minus T over T2 minus T1 and T minus T1 over T2 minus T1. And you can verify that that works to give you the first one if the 30-day mark falls at T1, and the second one if the 30-day mark is T2. And this is obviously linear in T, so that does the job. And then, once you've done this, just solve this equation for sigma T. So you have to divide this by T, then take the square root, and then the old VIX is 100 times sigma T. So it's expressed in volatility points, what traders think of as volatility points. The sigma is typically something, a number like 0.35, and multiplying by 100 makes it 35, and people talk about 35 vol for volatility. Okay, so that's the old VIX. Now, here's an issue with the old VIX. I believe that the SIBO was hoping that there would be so much interest in the VIX as a measure of future volatility that there would be a demand for futures on the VIX and options on the futures to be traded. But that demand never materialized because if we go back to this picture here, the old VIX is an at-the-forward implied volatility, essentially. And one thing we know about Black-Scholes implied volatilities is the Black-Scholes model is really not correct, and so there's what's called a volatility smile. So if you look at a given maturity, strike by strike, and find the Black-Scholes implied volatilities, they're all different. And so what's special about the at-the-forward volatility? Why is that one supposedly predictive of the future? So it was never clear what the value of that particular number was in terms of indicating something about markets. Although there's this phenomenon that when markets go down, people are panicked, volatility goes up, and when markets go up, volatility goes down. So it became useful as a talking point. A lot of financial advisors and Wall Street commentators used to call it the fear index. They probably still call it that, meaning when the VIX is high, people are kind of panicked, and they would give advice such as, well, they're overreacting. It's a good time to buy because the market is irrationally low, and when the VIX is low, then people are complacent, so maybe don't do anything. But now, in the 1990s, as I said, this financial engineering technology was developed, which is really quite beautiful and sophisticated, as a way to model variance swaps. But this turned out to be something that the SIBO could use to create a new VIX, and they did that and started publishing it in 2002. The new VIX depends on two financial discoveries or formulas. The first is Lewis Scott's log contract paper, which is, I think, about 1987. And a new calculus formula. This is kind of amazing and wonderful that there's a new formula in the 300-year-old history of the mathematics of calculus. Something new pops up in the 1990s. I call it the Carr-Madan formula, and this is my personal name for it. This name comes from the fact that the first place I read about it was in a little article in a quant journal written by Peter Carr and Dilip Madan. But I asked Peter about it one time, and he said, oh, everybody knew about that in the 90s. It was just in the air. So lots of people apparently realized that this formula existed, and had discovered it simultaneously. So we're going to talk about these two components and then put them together to see how to find the new VIX, how to calculate the new VIX. So the first thing is the log contract. So what was Lewis Scott doing? He was just posing the hypothetical question, what is the value of a European-style derivative security which pays as its payoff to the holder of the contract the log of the stock price at maturity? So this contract, if you own this contract, it does nothing until maturity, and then it pays you the log of the stock price. It's a little weird. I've never seen anybody trading such things, but he was asking this question more or less abstractly. Now, in no arbitrage pricing, we know that finding the no arbitrage price, which is the correct price for a derivative security, is the same as finding the discounted expected payoff under the risk-neutral probability distribution. So this little hat over the E is my reminder to myself and to you always that this is not the expectation using any kind of real probability for the future stock price. It's the expectation using the so-called risk-neutral probability density function for this future stock price, or in this case, the index price ST. And that risk-neutral distribution is, there's a lot of math behind that, but it's the distribution that's equivalent to finding the no arbitrage price. So this should be what we're after if we want to price the Lewis-Scott log contract. So the key question is, how do we find E hat of log of ST? Okay, so in order to do that, we have to make some assumptions about the form of that risk-neutral distribution. Or in other words, where does the risk-neutral distribution come from? It comes from the stochastic process for the stock. So Lewis-Scott is going to make assumptions about the underlying process for the index or the stock, in this case, the S&P 500 index. He's going to represent the stochastic process. Stochastic, by the way, just means random. That's all it is, random process. He's going to represent it by what's called a stochastic differential equation, or SDE. So that's why I wrote SDE here. And this is the differential. So the DST is the differential of the index price over a little infinitesimal amount of time dt. So literally it's just, well, when you get to time t, you know the index price is ST. We don't know what it's going to be dt time later, infinitesimally, an infinitesimal increment later, but we'll just call that difference dst. So this is a random variable. And the model for this is going to be, well, dst is going to look like R minus Q, so this is what makes it risk neutral. That's why R minus Q is here. Ordinarily, there would be some unknown drift that includes some risk premium, but here we're doing risk-free, risk-neutral pricing times STDT. And if you look at this and forget about the random shock over here, this says DST over ST is just R minus Q dt, and that's the differential, the ordinary differential equation for exponential growth. But then we add randomness to it. So the DWT is a standard Brownian motion increment. And you make this proportional to the volatility that you want and the stock price so that it's still modeling the return, DST over ST. Now, the question is, what do you assume about sigma? Well, Lewis-Scott wanted this to be very, very general, so he said, well, let's assume a stochastic volatility model, in which case you need a stochastic process for the volatility sigma. So you have to have another stochastic differential equation for sigma. So this is going to be d sigma t. So sigma t itself is random, which gives you a more realistic representation of the way things work in the world. Now, there are infinitely many choices possible for how you construct the SDE, or the process for sigma t. Anything can be, the beauty of this analysis is that anything works here provided that the sigma t sample paths are square integrable. That's really all you need. That's the only restriction you need. So it doesn't matter what form this takes. That's a wonderful feature here. Okay, so in other words, we require that these integrals exist for each path followed by sigma t. And those paths will be continuous because Brownian motion is a continuous process. Okay, so given this stochastic process for ST and sigma t, then the question became, well, what's the process for log ST? Because if we can find the random process for log ST, then we can find the probability distribution for log ST and find its expectation. And that's all going to be risk neutral because we put the R minus Q in there as the drift. Okay, so now I'm going to just use a Taylor expansion for the log function around the fixed point ST. Remember, once you're at time t, ST is known. st plus dt is the random piece, and so these differentials are random, but st is known. Now, remember from calculus that the derivative of log is 1 over x. The second derivative is therefore the derivative of 1 over x, which is x to the minus first power, so it's minus x to the minus 2, or minus 1 over x squared, and the derivatives keep going. The Taylor expansion is the first derivative times the change, this difference, plus half the second derivative times the square of the change, plus 1 over 3 factorial third derivative times the cube of the change, and so on ad infinitum. And if I plug these two into the first two terms, we see that we get 1 over st, that's 1 over x dst, minus 1 half, that's the half there, and times the 1 over x squared is 1 over s squared dst squared, and so on. And now we're going to ask ourselves, what do these terms look like? And a key point here is, how many of them are truly large enough to be considered? So we need to focus on a rule in stochastic calculus. So this is kind of a computational rule in stochastic calculus. Since dt is infinitesimal, dt to a power that's bigger than 1 is 0. We wipe it out. The basic intuitive understanding of this is, if I were calculating derivatives, so I'm taking like ds over dt of this random quantity, and I'm calculating the derivative of some function of s, well, when I calculate the numerator, the ds, the differential of s, or differential of the function of s, if there are terms in it with dt to a higher power than 1, dt to the epsilon, then when I find the derivative by dividing by dt, that divided by dt is going to be dt to the epsilon minus 1, which is still a positive power, and in the limit, because these are infinitesimal, they're really zeros, the dt's, that goes to 0. So those terms disappear. They don't count. So this is our rule of thumb. Now we have to ask, well, what's the order of magnitude in terms of dt of these terms we're looking at? What's the size of dst? What's the size of dwt? So remember, the increment of Brownian motion at time t is the future wt plus dt minus wt. And the reason we call it standard Brownian motion is that it's normal with mean 0, standardized to mean 0. And standard deviation, I'm going to put the standard deviation as the second parameter of the normal distribution here, square root of dt. Wt itself is normal with mean 0, standard deviation square root of t. So the variance is t. Notice that W1, for 1 unit of time, W1 is standard normal, n of 0, 1. That's why we call it standard Brownian motion. Okay, so knowing that, we can ask about sizes. So what is the size of a random variable like dwt? Well, a random variable you can think of as something in function space or just a vector. And how do you measure the size? Well, the L2 norm is a standard measure of size. And what is the L2 norm of a random variable? Well, it's the square root of the mean of the squares, the expected value of the squares. That's the standard deviation. So the standard deviation is the measure of size. It's the L2 norm of dwt. And so that's the square root of dt, or dt to the 1/2. So that, in stochastic calculus, dwt stays in all the equations. Okay, but now we can start looking at things like dst squared. So notice in our stochastic process, our random process for the stock price, dst is r minus q st times dt to the first power. That's not a prime, that's the first power, plus sigma t st dwt, and this is of order dt to the 1/2 power. So the overall size of dst is, or the order of it, is dt to the 1/2 power. Okay, so what about dst squared? Well, if you square this, notice the first term squared is dt squared, which goes to 0. That disappears. The cross terms, when you square it, are dt to the 3/2, power bigger than 1. That goes to 0. So those are gone. So dst squared actually reduces to just the square of the last term, which is going to be of order dt and should survive. Okay, what about the cubes? Well, luckily for us, and wonderfully, all the higher powers go to 0. So we don't need all those extra terms in the Taylor series expansion. They just disappear. We only need those first two terms, which is why I only wrote those two down here. These are the only two terms we get in d log st. So now we're going to compute those. So dwt is normal with mean 0, standard deviation square root of t. If I take a normal random variable minus its mean, which in this case is 0, and divide by the standard deviation, that standardizes it so it becomes a standard normal, which we can call z, because everybody thinks of z as the name of a standard normal. Well, the z squared is always chi squared with 1 degree of freedom. And we know about the chi-squared distribution. Its mean is 1, its variance is 2. So now we know the mean and variance of the square of dwt over the square root of dt. The mean of dwt over square root of dt squared is 1. And if you do the algebra here, you get that the mean, the expectation of dwt quantity squared is dt. When you square this, the denominator is just dt. Likewise here, you have dwt quantity squared divided by dt. Now, with the variance, when you factor out a constant, it's squared because the variance is the expectation of the square of something. Okay, that means that the variance of dwt squared is going to be 2dt squared. But this is stochastic calculus. dt squared is 0. This thing has variance 0. Variance of dwt squared is 0. That means it's a constant. And if it's a constant, then the mean is that constant. So we now know dwt squared, speaking in stochastic calculus calculations, is dt. So we can now substitute this back into our formulas because dst squared is now sigma squared s squared dt. So in these two terms, the only surviving terms, we have 1 over st times the first term, dst. That just cancels out the s's from the stochastic differential equation for s, leaving r minus q dt plus sigma t dwt. And then here, we're dividing by st squared. We have the minus 1/2, and that gets rid of the s's, the st's in the dst squared. Those are squares. And that's just sigma t squared dt. So we get minus 1/2 sigma t squared dt. So this is the SDE for log st. Now there are two random pieces here. This part is random, and that part is random. Now we're going to integrate both sides of that equation. So if you look at this equation, we're going to integrate this, and we're going to integrate that, and we're going to integrate them as time goes from 0 to big T. Well, what's the integral from 0 to big T of d log st? Well, now we're just adding up differentials. And the differentials, each one is like log st plus dt minus the previous st, log st. That's a collapsing sum. And so it's just the last term minus the first term. Even though this is a random quantity in here, we can still add these up because the differentials form this collapsing sum, and we just get this. It's still random because s in the future, st, is random. Okay, then the other three, on the other side, we have the three terms to integrate. This is deterministic. So the integral of this is just r minus qt. That's just simple calculus. This is an integral of a random path, and this is an integral of a random path, so those are just random. So we have the random log st, we could write as the log of s naught plus this, and then plus these two stochastic terms, random terms. So the next step in the technology development here is we're going to take risk-neutral expectations of all these things. Okay, well what we have so far, rewriting this, is the log of st is the log of s0 plus r minus qt plus these two integrals. One thing I want to note right off the bat here is that if you look at log of s0 plus r minus qt, that is the log of the forward price. So we can just summarize that as log of f. And then we have these other two terms. Now, we're going to take the risk-neutral expectation of this. This is a constant, so it's just that constant. And then we have the risk-neutral expectation of this integral. Because expectation is an integral, and we have Fubini's theorem that says we can switch the order of integration, or in calculus, you know that with double integrals you can switch the order of integration. We can move the expectation inside the integral. And here I'm going to leave the expectation outside for a certain reason. And now Lewis Scott is kind of stuck. He says, okay, I've got this integral here of this expectation of this product. I don't know what to do. And you can see what's going to happen here. He's going to make another assumption. In addition to stochastic volatility, he's going to assume that sigma t, the sigma t process is non-anticipating with respect to dWt. And essentially what that means, we just need to know that it means that sigma t is independent of dWt. The thinking being sigma t is determined at time t. It becomes a constant. And so this, which is entirely in the future from time t, it comes after t, shouldn't really depend on this. They should be independent. Now, again, this is something you could argue with. But it's not crazy to assume this. And since it's not crazy, it gives us an avenue for simplifying the result here. And you can see what happens. Once these are independent, the expectation of the product is the product of the expectations from basic probability. And the expectation of Brownian motion is 0. So this whole integral disappears under this assumption. And now we have this beautiful formula. E hat log st is the log of the forward minus 1/2 the expectation of this integral. And now suddenly, okay, so this is kind of the end of the discussion of the log contract for Lewis Scott, I guess. But it's an incredible discovery because of this term. If we rewrite this to express that term in terms of the other two, what do we have? We have an expectation of future realized total variance. Notice sigma t squared dt, that's, since volatility is stochastic, that's the infinitesimal volatility or infinitesimal variance that's going to occur in the time interval from t to t plus dt. And if we add up all those infinitesimal variances, we get the total variance that it is going to be realized from 0 to t. It's random, and here we're calculating an actual mathematical expectation of future realized variance. It's the risk-neutral expected future realized variance. This is amazing. This is amazing. And we can express it as 2 times log of the forward minus the risk-neutral expectation of the log of st. So this is really tantalizing because it says we could get a really mathematically sound estimate of future realized volatility during a fixed time period if only we could calculate the log contract future value E hat log of st. So that's brilliant. Now, once we are able to do that, which we'll be able to do in a few minutes, I want to think of this risk-neutral expected future realized variance as the average annualized variance, sigma t squared, times t. Right? That would, if I had an annualized variance for that time period, this would be the total variance in that time period. So sigma t bar would be the average annualized volatility that's going to be realized in the future time period from 0 to t. So substituting that in here, we have this equation, and solving for sigma t bar squared, we get this. And this is really the key to variance swaps. But we need to be able to fill this in. Okay, so the next part is the Carr-Madan formula, because that's the key to filling in the expectation of the log of st. Okay, so this, as I said, I don't know exactly the origin of this. It seems to have arisen naturally in the 1990s. But it's basically a theorem in calculus. And it really belongs in two textbooks as an exercise in the section on integration by parts, because that's how we're going to prove it. So here's the theorem. The theorem says, let f of x be a twice piecewise continuously differentiable function on an interval ab. It can be any interval. Pick any fixed point x naught in ab. Then, for any x in ab, we can represent the value of the function f of x as f of x naught plus f prime x naught times x minus x naught. So this is like the Taylor expansion, the beginning of it, but we cut it off there and replace everything else by these two integrals. The integral from a to our fixed cutoff point times y minus x plus. Y minus x plus is the positive part. That's the maximum of that number and 0. So it's y minus x if y minus x is positive, and it's 0 if y minus x is negative. So it's the integral of y minus x plus times f double prime of y dy plus the integral from x naught to b of x minus y plus, the positive part of that, times f double prime of y dy. So notice we're using the function, the first derivative, and the second derivatives, and you can see why we basically need f double prime to be integrable for this to work. Okay, that's the theorem. We're going to give a quick proof of it in a second, but first, let's take a look at what it says that's really incredible. So what is x minus y positive part as a function of x? Because if you go back to this, you can think of this as saying, okay, I've got this function of f of x. I can express it as a constant plus a linear function of x, and then I can think of the y minus x plus as a function of x. For each y, I have a different one, and I'm adding up. This integral is like taking a big linear combination of these functions with these coefficients. And over here, I've got a big linear combination of the x minus y plus functions of x with these coefficients. So this says f of x can be represented as a constant plus a linear function plus linear combinations of those functions, those y minus x and x minus y plus functions. Well, as a function of x, y is fixed, and this is what that function looks like. As a function of x, y minus x plus is this one. And immediately you see that this looks like the call payoff function for the payoff of a call at maturity, and this is the put payoff function. Peter Carr, by the way, who was Canadian, was a huge hockey fan, and he used to always refer to these two pictures as the hockey sticks. So the call and put payoff functions are the hockey sticks. So we've learned that every twice piecewise continuously differentiable function can be represented as a big linear combination of hockey sticks and a constant. And a linear function can always be written as two hockey sticks, a call minus a put with the same strike. Okay, so here's the proof. We're going to divide this into two cases. Notice in the theorem, we only have to verify this as an identity for a fixed x, for each x separately. So we're going to do this one x at a time. Case 1 is when x is less than or equal to x naught. Case 2 is x bigger than x naught. So in case 1, let's notice that the second integral goes from x naught to b. Well, x is less than or equal to x naught. So y is the variable of integration. It goes from x naught to b. If x is less than or equal to x naught, y is always bigger than x, because x is below x naught for this fixed x we're talking about. And therefore, this is always 0. So the second integral disappears. It's gone. What about the first integral? Well, the first integral goes from a to x naught, and it's y minus x plus f double prime y dy. Now, x is less than or equal to x naught. It's bigger than a because it's in the interval. But notice, for the y's below x, this is 0. So we only have to integrate from x to x naught. And between x and x naught, y minus x plus is just y minus x. And now this integral of y minus x f double prime of y dy, is a perfect candidate for integration by parts. What is integration by parts? It's the reverse of the product rule for derivatives. Here's the product rule for derivatives written in differential form. If we rewrite that as u dv is duv minus v du and integrate both sides, we get integration by parts. Integral of u dv is uv minus v du. Well, in this integral, We can choose u to be y minus x as a function of y, because we're doing an integral of a function of y. The x is fixed. dv we'll take to be this. Well, for v, we need an antiderivative of that. Obviously, an antiderivative of f double prime is f prime. The second derivative antiderivative is the first derivative. And then the derivative of y minus x with respect to y is du is just dy, because that's linear. So now, applying integration by parts, that's going to be equal to y minus x f prime of y evaluated from x to x naught minus the integral from x to x naught of v dy, which is f prime y dy. Well, this integral is just f of y evaluated from x to x naught, so we get this. Here, if I substitute in x naught for y, I get this. When I substitute x in, it's 0, because this is y minus x. So here are the terms. Well, notice this is just f of x minus the first two terms in the Carr-Madan formula. So they cancel out and the identity holds. We just get f of x on the right-hand side. Done. This is so cool. This is amazing. Case 2 is similar. In that case, the first integral becomes 0. The second integral gives you this identity. I'm going to let you figure that out for yourself if it isn't already clear to you, but you can work this out. It's a good exercise, but so cool, really so cool. 300 years of calculus and nobody saw this. Why is that? Well, my guess is nobody ever thought about using the hockey sticks, right? Who would use that? Option traders would use that. Option quants would use that. Okay, so now we're going to apply the Carr-Madan formula to derivative securities. So in order to make it mentally more absorbable, to facilitate grasping this, I'm going to change the notation in the formula. I'm going to let x be the future index or stock price. I'm going to let y be a generic strike price, k, and here's a little mistake, but there it is. X naught is going to be a fixed strike, which we're free to choose. Notice in Carr-Madan you can choose x naught to be any point. Now, what am I going to choose for A and B? Well, I'm working with a variable that represents a stock price or an index price. Those prices just go from 0 to infinity. So I'm going to choose A to be 0 and B to be infinity. So having done that, the Carr-Madan formula is rewritten as f of st is f of k naught, our fixed strike, plus f prime at k naught times st minus k naught, that's our x minus x naught, plus the integral from 0 to k naught of k minus st plus, that's the put payoff function, f double prime of k dk, plus the integral from k naught to infinity of the call payoff function, f double prime of k dk. So that is amazing. It says if you have a European-style derivative security, which is entirely defined by what it's going to pay you at maturity only, so that's f of st, it's of that form, then you can express that payoff function as a combination of a constant linear payoff, this is like a forward contract payoff, and put payoffs and call payoffs. So puts and calls are fundamental. So now we want to take the risk-neutral expectation of both sides, and this is where we're going to do pricing of things, option pricing, or derivative security pricing of general derivative securities. So E hat, the risk-neutral expectation of f of st, is then the expectations of these. Well, this is a constant, so that's its expectation. St in the risk-neutral world has expectation the forward price. So this is f prime of k, k naught, f minus k naught. Now, as before, using the ability to switch the order of integration, we can push the expectation inside the other two integrals. If we integrate the put payoff function, what we're going to get is the expected payoff of the put at maturity. That's the forward value of the put. So I can express that as e to the RT, the forward value of the current put price. So that expectation becomes that. And similarly, in the second integral, it's the call payoff function. And so when I take the expectation of that, I get the value of the call at maturity. That's the forward value of the call price today. So I can express this in terms of put and call prices. So just looking at this line here, this is just stunning, right? It says, look, if you want to price some weird derivative security with a weird payoff function, it's a European style security, all you need to know is the market prices of puts and calls, because you can just add those up weighted by the second derivative of that function and add these two terms. You need to know the forward price, and boom, you're done. You don't need to go through any big contortions. So now, finally, we apply that to the log of ST, and we can achieve the Lewis-Scott vision. E hat of log of ST, well, we have to put in the derivatives of the log function. Well, the derivative of the log function is 1 over, so we're going to get 1 over k0. So the first term is just the log of k0 because the function is log. This is 1 over k0. I'm going to write that whole thing as f over k0 minus 1 for a particular reason. It'll be good to think of it this way. And then the derivatives here are minus 1 over k squared. So in these integrals, we get minus integral from 0 to k naught of e to the RT times the put divided by k squared dk, and similarly for the calls. This is the famous 1 over k squared weighted portfolio of puts and calls that's involved in variance swaps and in the new VIX. And now we're ready to put this into our formula for expected future realized volatility, or variance. So here's our expected future realized variance. I left the bar off that. There should be a bar on there for averaged annualized volatility, but it's 2 over t log f minus this expectation. So substituting in our newly found value for this via Carr-Madan, it becomes 2 over t times the log of f minus the first term, which is log of k0. I've summarized that here as log of f over k0, because the log of a quotient is the difference of the logs. And then I have to change the sign of the other term. So I'm subtracting this instead of adding it, and adding these instead of subtracting them. So here's our nice formula. And this is what you can use to calculate sigma t bar squared ti for any time. And formulating the new VIX, we're going to choose 2 expirations, 2 S&P 500 option expirations, surrounding the 30-day point. And this 30-day point is going to be our t that we're after. But we have to separately, because we only have option prices for fixed maturities, we have to separately calculate the expected future realized variances for T1 and T2, and then interpolate time linearly to get the one in the middle. That's how you do the new VIX. So the new VIX is then 100 times sigma t. You just do the time linear interpolation just as we did in the old VIX, and then you solve that equation that gives you sigma t squared t. You solve it for sigma t. And notice it involves 100 times the square root. So this is the new VIX. That's what they publish. Now I want you to just take a minute to notice something. You could also have a bone to pick with this, which is perfectly reasonable. We've gone through all this and realized that this is the actual expected risk-neutral, expected future realized variance. So sigma t squared is the actual expected future realized and annualized variance, the annualized value of that expected variance. So that's sigma t squared is an expectation. And now we're expressing the VIX as 100 times the square root of an expectation. Well, you could worry about the square root of an expectation not being the expectation of the square root, and that's perfectly reasonable. But this is the choice the SIBO made in how to calculate this and publish it. So it is this 100 times the square root of the expectation. Now, if we're going to talk about the new VIX, there are various computational details. How exactly do you do this? Because after all, these integrals assume a continuum of put and call prices from the market for all strikes K over all real numbers K. Well, those don't exist. Puts and calls only exist at discrete, well-defined strikes. There are only a finite number of them. You can't literally do these integrals, so you have to do numerical approximations to the integrals. And there are other numerical choices to be made here. So I'm just going to go through some of the SIBO details. One of the interesting first details is they decided for some reason to replace these two terms by a single term. And what they're doing is using the approximation of log of 1 plus x, that function, by x minus x squared over 2. These are the first two terms of the Taylor expansion of log of 1 plus x. They cut it off. The next one would be plus x cubed over 3. It's alternating. And then let x equal f over k naught minus 1. That's why I wrote it that way before, because if you do that, the log of 1 plus x is the log of f over k naught. And then this expansion says, well, that is approximately f over k naught minus 1 minus 1/2 f over k naught minus 1 squared. So the log f over k naught minus this term that we saw in that formula is really just this term if you assume this approximation. And so the SIBO rewrites it as expected future realized variance in the time period 0 to t is 2 over t times this term. So it's one term instead of two. And then they write the integral as the integral from 0 to infinity of e to the RT q of k over k squared, where q of k is the midquote. So they have to choose, what is the price? What is the market price of the option? Well, they're saying, I don't know, let's make it the midquote. After all, in the market, you don't get a single price. You get a bid and an offer, and there's always a gap there. The market makers spread. So they say, let's use midquotes. And then the question is, how do you numerically do this integral? And by the way, at the forward, for the at the forward strike, they replace, so below the forward, these are midquotes for the puts, and those are the sort of the out of the money puts. Above the forward, it's the midquote for the calls, the out of the money calls. At the forward, they actually take both the call and the put price and average them. So that's what Q of k stands for. But how are you going to do the numerical integral? Well, they're going to do a numerical integral over all the existing strikes, except for some we'll exclude in a second. So it's going to look like the value at that strike times a delta ki. Now here's their choice for delta ki, and their white papers don't explain this choice, but if you understand the trapezoidal rule, it'll jump out at you immediately that that implies what they're using. That's what they're using. So they're using the trapezoidal rule. That means their delta ki should be this quantity, ki plus 1 minus ki minus 1 over 2. Okay, so they've chosen the trapezoidal rule. Another choice they make is to choose k naught as basically the first strike below the forward, and I put a star here, they use a very clever way of calculating the forward price. With the S&P 500 index, the forward price can be kind of tricky to calculate because there's this stream of dividends that comes with it, and you'd have to kind of statistically estimate what that's going to be. Instead, the SIBO basically leverages the market and says, well, we know these are European options, so put-call parity applies. And so what we'll do is just say the forward is the strike plus e to the RT times the call minus put. This is put-call parity, and we'll choose the K close to the, basically close to the forward price itself. And in other words, they're just assuming that the market makers have got the call and the put prices right. In other words, they've done all the work to find out what the dividends are and so on, and they'll just piggyback off that and say, okay, the market must have the forward right, so here it is. That's a very clever approach. They also have rules that say, well, if a call or put option has a zero bid, that means the bid price is zero. That really means we don't know what the price is, so don't use those, throw those out. And if you go up marching up the call strikes, if you hit 2 zero bids in a row, stop, don't include any strikes above that, and the same thing going down with the puts. Once you hit 2 zero bid puts in a row, stop, don't include any further strikes. Anyway, at this point, you have all the information you need to go to the SIBO website, read their white papers on the VIX, and by the way, they have now proliferated their VIX on many, many different indices, many products. And I wanted to mention that after they started publishing this in 2002, there was demand for trading derivatives based on this. So in 2004, the SIBO launched the VIX futures with Susquehanna as the specialist, the primary market maker. And we had to get all of this stuff encoded in a model and a trading application. And then later, I think around 2006, they also introduced options on the VIX futures. So we now have VIX options, VIX futures. And by the way, that's really interesting because once you have options on something, you can do this whole calculation to calculate the VIX of that thing. So there can be a VIX of the VIX, and there is. Anyway, now you should go out, read the VIX white papers, and you can also read about variance swaps. There are plenty of papers and white papers about those. So that's all for today. Thanks for watching. And if you'd like to see some of my other lectures, they will be posted on Susquehanna's YouTube channel. Thank you.